quote from, I guess, one of the heroes of stellar physics. And this was a guy called Sir Arthur Eddington. And he wrote a sort of textbook in the 1920s called The Internal Constitution of the Stars. And I understand you may not have actually read this particular work. It's quite a heavy piece of work, but it's definitely one that we now look back on as one of the really seminal pieces which laid down how we actually understand how stars work. So it's a really, really important foundation piece of work in our field. So in the Internal Constitution of the Stars, Sir Arthur Eddington writes, "What appliance can pierce through the outer layers of a star and test the conditions within?" And I guess he's really talking in the rhetoric here. He doesn't really expect there to ever be a way for us to be able to probe deep down into the interiors of stars, because let's face it, we all know stars really, really far away. And even our nearest neighbor, the sun, really close, but not really something we're sending a whole lot of probes into, right, to try and figure out its interior. So in the view of Arthur Eddington, he couldn't really see a way that we could possibly do direct measurements of what actually was going on inside of a star. This was really going to be a realm for theorists and theorists only. But I'm very, very pleased to say it didn't even take us 100 years before we figured out how we might even be able to do this. And actually, it's really been in the last sort of 20 years that this particular field of asteroseismology has taken off and been able to start to understand how we might do this and how we do this now. So coming back to the title of this talk, which is The Music of the Stars, I wanted to relate what I do in asteroseismology to the physics of music, because they're actually really, really similar. And music is kind of something that lots of people have experience of. Some people are brilliantly talented musicians. I'm sure many members of the audience are really talented musicians. I'm not by any stretch of the imagination. I can only do star music, but I do know a little bit of music theory. And if you've sort of thought about music a little bit before, and especially if you've thought about physics of music and how actually sound works, then it's kind of a nice segue into how we understand stars. So what we have here are some musical instruments. Now I'm going to play you a note, and hopefully you can hear this note nice and loud and clear. And it's a note that's being played on a violin. Let's see. Oops, not that one. Let's go here. Great, so that's a note from a violin. It's at a B above concert A, which I think I know what that means. I'm sure lots of the audience will know what that means. And if you look into exactly what frequency that note is being played at, it's at somewhere around 497 hertz. So that means that the violin strings are sort of wiggling at about 497 times per second. So pretty high frequency sound. Now, it's really interesting because you can play that same note with other instruments in the orchestra, and you can actually tell, even if you're not a musician, you can tell that different instruments are playing the same note. So here I've got that exact same note being played by a trumpet. And you can tell that's a different instrument, right? But hey, isn't that just playing the same note? Isn't it still playing this B above concert A, this 497 hertz? Well, what's actually happening is that the instrument is not just playing that single frequency. And this is what the graph I've got here is showing. It's actually playing a whole lot of frequencies at the same time. So although you have the main frequency is set at a particular hertz, then you also have lots and lots of repetitions of this frequency that we call harmonics. So you might get twice the frequency, 3 times the frequency, 4 times the frequency. And how strong all those harmonics are in that spectrum gives you the particular sound which tells you it's a violin, or the particular sound that tells you it's a trumpet. Because if you just get a computer to sit there and play that exact same note and play it at exactly that frequency, which is this one, it's really boring, right? It's like there's no character to that sound. So you need to have these other frequencies which are excited at the same time to get the real richness that you get out of a note that's being played on a musical instrument. So this graph here is called a frequency spectrum, and here you can see we've got 1, 2, 3, 4, up to 10 harmonics that are being played by this particular violin. And where I'm going with all this is that when you have lots of different frequencies that are excited in a musical instrument, this is a little bit like how we can look at lots of different frequencies which actually are excited in a star. And just in the ways that you can look at different frequencies excited by an instrument and tell the difference between a violin and a trumpet, then you can actually look at, say, different frequencies excited in a star and tell something that's unique about that particular star. So that's the real big segue into the music of the stars. And I'm going to tell you how we sort of look at these stars and try and figure out what actually they are doing in their pulsations and their frequencies. So first I thought it would be useful to come back to the seismology part, the waves. How does this all link to sort of waves in physics? And it's quite useful to think about waves that we see in different dimensions, because this starts to get us sort of warmed up and thinking about how pulsations work. Because if I just started and just imagine a three-dimensional wave, that's actually a really hard thing to imagine off the top of your head. So I think it's kind of easier to start off thinking about one-dimensional waves. So you might imagine a piece of string, and that piece of string is glued down at each end. And when you vibrate this piece of string, you can vibrate it in lots of different ways. You can vibrate it like we have in the top left-hand corner here, where you've just got the string that's bouncing up and down. But you can also vibrate it in ways where you have what we call nodes or stationary points. And so in the second one, which is in the top right, then you can see there's a single node in the center. And as we go through going down and across, then you can see lots more nodes are being added as we go along our wave on a string. Now, you can also, of course, make the analogy of this as a bit like actually playing your violin string, right? So you can vibrate the string of the violin. It's going to vibrate with different nodes depending on where your fingers are on the frets, and therefore you're going to get different frequencies produced by the strings of the violin. Now we can take that analogy and put it up into 2 dimensions now, and so we can look at how waves travel on a surface. So again, if you're musically inclined, you can think about how this might be like the surface of a drum, for example, that you've hit. Now, instead of having a single point, which is a node like we had on the string, here we've got actually circles or rings, lines, which are nodes. So you can see there's kind of a bit which is halfway out from the edge to the center of the drum. That doesn't really move, and then the edges move and the center moves. So you can set up different waves. Oops, there we go. Different waves on a drum with different patterns. So this is another type of pattern you can set up where now you've got some radial lines, which are the nodes. And you can see different parts of the drum moving up and moving down. So now using this pattern, we can wrap that around in our minds into a sort of a ball, and that's how we can create a 3-dimensional wave. So this is what that might look like if you have a nice big ball that's now pulsating with a 3-dimensional wave. And one might even call this a pulsating star, which is quite exciting. So now our nodes are like circles. They go around the whole surface of the sphere. Now, I have to be really honest with you and tell you that there's no pulsating star that looks quite as dramatic as this particular one. I think actually that would be fairly terrifying if you found a star that was pulsating this much. But this is the kind of thing that we're using to model how we understand these surface variations. In reality, these are very, very small surface changes that we're able to pick up. And indeed, that's kind of why I'm so excited about asteroseismology now, because these surface variations are very, very small. And it's only been in the last 20 to 30 years that we've even been able to detect them on the surfaces of stars. And it's only through some really brilliant new instrumentation and new techniques that we've been able to do that. So let's have a look at the 2 main ways that we can sort of try and pick up these frequencies and these patterns of pulsations that we have on our stars. So the first way that we can actually figure out that stars are pulsating is to look at their brightness. Because remember, when we're doing astronomy, there's only one star that we're really able to kind of look at the surface of in really great detail, and that's the sun. So if you're interested in any one other of the hundreds of billions of stars in the universe that's not the sun, you're kind of a little bit limited in the kind of observations that you can do. So we've got to look at basically what we receive here on Earth. And one of the ways that we do that is looking at the brightness of the star itself. We call this photometry, or the measurement of the light that we're receiving. And because the pulsations are quite small and only making very, very small changes on the surface, then it's taken us decades and decades of work to be able to get telescopes that are sensitive enough to be able to pick up these kinds of pulsations. So one of the first big heroes, if you like, of asteroseismology is actually a space telescope that you might more readily associate with another field of astronomy, which is planet hunting, and that is Kepler. So the Kepler Space Telescope flew from 2009 to 2013, and it turns out that planet hunters were interested in looking for really, really tiny changes in brightness, which happen when a planet passes in front of a star. And so astroseismologists came along and sort of said, well, hey, you're building these wonderful instruments that are able to detect tiny, tiny changes in brightness. We're really interested in that as well. So there's a real kind of nice community feel to these kind of telescopes, because they're not just planet hunters who are using them. Actually, lots of different communities use them, and astroseismology is one of the main users of space telescopes now that are doing these very, very sensitive planet hunting missions, but now also pulsation hunting missions. So Kepler was massive, massive success. And we're now in the era of TESS, which is the image on the right. So TESS is the Transiting Exoplanet Survey Satellite. Again, really nice that our friends in the exoplanet community had lots of money to stump up for a brand new space telescope. Not going to complain about that. And so TESS has been flying for just over 3 years now, and looking at some of the nearby stars in our galaxy, so ones that are fairly close to the sun, and again looking at the brightness changes in really, really minute detail. And TESS was particularly exciting to me because it works on the same stars that I work on from my ground-based telescope research as well. So we've now got a space telescope doing some really, really lovely work. And this is an example of the kind of thing that we're actually looking at when we look at the brightness changes of stars from space. So this is one of my very, very favorite stars, actually. You might not know it particularly well, specifically not when it's got this lovely catalogue number TIC 219234987. Maybe it is your favorite one. I won't judge too much, but I can't claim that astronomers are really good at naming things necessarily. But anyway, this particular star, what you're looking at here, the red line, is that you're looking at over time, which is on the x-axis. So each of those sort of markers is a day. So over the course of about a month in this whole graph, you can see that the brightness of the star, which is what's happening on the y-axis, is changing pretty dramatically, right? So it's going up and down and up and down and up and down and up and down. So it's getting brighter and fainter and brighter and fainter. Now, there's a really nice pattern that you can pretty quickly see there. It looks like you've got something happening that's sort of happening every, in this case, it's happening about every 1.4 days or something like that. But you can also see that there's something more going on than just that kind of up and down every 1.4 days. Sometimes the whole height goes down really, really quiet. So say in the middle here, it's actually still going up and down, but it's quite quiet, right? And then at the end, it's like gone a bit nuts, right? It's kind of really, really bright, really, really faint. It's all gone a bit crazy. And this is not something to do with the instrument. It's nothing to do with the precision of our measurements. This is actually the real star doing things. And what's really exciting is this means that the star is not just pulsating in a single frequency. It's not just playing a single note, if you like. There's actually lots of frequencies layered on top of one another. And those frequencies are all interacting. So sometimes they interact together and cancel each other out, which is when you get less brightness. And sometimes they work together and amplify the brightness, so it becomes much, much brighter. So I find this really, really exciting, this kind of graph, because this says, you know, there's something really cool going on with the star, and there's lots to dig down into and figure out about it. So that was the first way that we can look at pulsations. We can detect what's the brightness changes that are happening on the star. The second way we can do it is actually kind of an interestingly direct way of looking at how surface motions work. And that is using spectroscopy and using an effect in physics called the Doppler effect. Now, you might be familiar with the Doppler effect. You might have been studying it. You might have been doing it for ages. Or you might only be familiar with the kind of, I guess, the very classic way that we tend to see the Doppler effect manifest in our everyday lives, which is things like sirens, which become higher and higher pitched as the particular siren emitting vehicle gets closer and closer to you. So what's happening there is the sound that's being emitted by, let's call it a fire engine, gets squished up because the whole fire engine is racing towards you. It squishes up the waves. And that means that they get higher pitched. And then as it moves away from you, the waves get sort of pulled apart. And so it becomes lower pitched. But we don't just see the Doppler effect in sound, we also see it in light. So again, we're measuring the light from stars, but we can use the Doppler effect to look at what's happening on the surface. And what we're doing is, I'll put up this little blobby star again to help you imagine. What's happening is when the surface of the star moves towards you, actually the color of the light that's coming from that star becomes a little bit bluer. And then when the surface of the star is going away from you, the color becomes a little bit redder. And so we can actually measure this, and we can say, look at the star and measure it become a little bit bluer, a little bit redder, a little bit bluer, a little bit redder. And that gives us exactly the same pattern as what we would see in a brightness change, except now we're directly measuring actually the surface of the star moving towards and away from us. And it's kind of at this point that I often have to take a step back and say, this is a little bit nuts. We're measuring the surface of a star that is hundreds of light years away, moving maybe a few kilometers up and down over time. And that is just an astounding, I think, progression of technology that we can do that now. It's nuts, you know, that we can measure that so precisely. Yeah, so what I do in my ground-based work is, this is the observatory I work at mostly. It's the University of Canterbury's Mount John Observatory, which is located in the middle of the South Island of New Zealand. And as you can see from the picture on the left, it's actually very close to a lot of the filming locations that you may have seen in Lord of the Rings. It really is in a really gorgeous part of the country, gorgeous part of the world. And we have a telescope there that we use very heavily for asteroseismology. So it's a brilliant instrument. It's the one in the photograph behind me. It's a 1 meter telescope, so a fairly modest size. But what we actually have that's brilliant about that is we have a very, very high resolution spectrograph that we use on that telescope. And it's that very high resolution that we can use to measure these very, very tiny changes in the colors of the star as we see the Doppler effect on the surface. So it's very exciting that we can then start to take those pieces of data, whether we're taking the brightness changes or whether we're taking the color changes from the star, we can track the frequencies of the star as they happen. And so what you've got here in the blue line, this is actually a frequency spectrum of the same star that I showed you before, the red brightening dimming star. And you can, if I've got the violin frequency spectrum down below, you can start to see maybe that how those two are actually linked now. We're seeing in the star lots of frequencies that are excited. Sometimes we're even seeing things like harmonics, just like you would see in a violin. But we're also seeing other little bits that are giving kind of each star its unique character. So in this particular star, sorry, we've got a really strong frequency, which is this one here at this 1.3, 1.4 cycles per day. So it's a nice star. It's, you know, pulsating in just in a couple of days. It's a really nice time for astronomers. You know, it's not too quick, it's not too slow. You don't have to wait for too long, but you don't have to always have a clear night, which is useful. And you can see this frequency is actually related to these other ones. You can see they're nicely equally spaced, like the violin spectrum. But there's also hints of other frequencies, like this one here, that are starting to pop out in the data. And these are the ones that, again, are giving that really just more than one frequency in the star, which is what we really, really look for. So once we've taken all these frequencies and sort of figured out, okay, well, these are all the different frequencies that the star is pulsating with, kind of, so what, you know, what does that mean? How do we do some more science with that? Well, the first thing we want to do is actually track and sort of figure out what each frequency means for how the surface of the star is pulsating. Because I showed you before with these three-dimensional spheres, just one example of the kind of shape, the geometry in which a star can pulsate. But it can pulsate in all some sorts of weird and wonderful ways. So this is another way. This is one of my favorites. The Bobby star, going different parts of the star, moving in, moving out. It's all very exciting. So you might have one frequency that has this kind of geometry on the surface of the star. But you might have another frequency that has a slightly different geometry. And this one looks a bit more dull. And it's actually, I mean, I don't know what sometimes the universe says weird things, but this is actually the most common frequency that we find in our pulsating stars. And it's the most simple one in a way. So it's just two hemispheres, one going out, one going in all the time. So most of the frequencies that we do see in our pulsating stars are similar to this one, which is, I mean, it's nice. Sometimes you don't want too complicated, right? It's a little bit too hard to disentangle. But you do get the odd one that's a bit crazy, like the first one. So once we've gone from measuring our frequencies, we can then fit our models and try and figure out what each mode, what geometry each of those frequencies is exciting. And then we can get to, I guess, closer to what we're actually trying to do in terms of the science, in terms of the physics. Because it's all well and good in any type of science to do your measurements and to get those nailed and correct. But then you've got to figure out what on earth they mean, right? So that's where we've got to take to the next level and look at how do we figure out what the surface of a star is telling us about the internal structure. Because with stars, all the light that we're receiving, all those photons that are coming from the star in terms of the brightness changes, and even all the photons that are coming from the star in terms of the color changes, they're all coming from the surface. So they're telling us what the surface is doing, but we want to know what's going on inside. Remember, we're trying to figure out this deep internal structure of this kind of impenetrable object in the universe. And the way that we can actually do that is by considering actually the origins of these pulsations. So these are not pulsations that are kind of waves trapped on the surface. They're actually pulsations that originate from very, very deep within the star. So this is a nice graphic. If you imagine it's kind of a big cutaway where we've got some pulsations that are happening in the core. But what I'm interested in looking at is actually the sort of the outer part of that. Let's watch that again. This kind of slice here. The pulsations start off very, very near the core, and then they actually propagate through most of the interior of the star before making it out to the surface. And that's really important because that's a wave traveling through a medium, or it's a wave that travels from near the core of the star all the way out to the surface. And it carries with it the information of the physics of the interior of the star. It can't not, right? It's affected by the fact that it's had to travel through the star. So it brings that information up to the surface. And that's what we can then figure out what's going on inside from the way that these surface pulsations, or way these pulsations behave on the surface. So that's the really exciting thing. We've found this probe, this mechanism that's going to bring information from the interior of the star all the way to the surface. Now, I guess in some ways I've kind of made this sound like a done deal. It's like, bang, do your observations, put your space telescope up there, go to your observatory, take some data, then, you know, look at the frequencies, look at the modes, then you figured out what's going on inside the star. Well done, you can have a cup of tea and go to bed. It's always a little bit more complicated than that, isn't it? So we are doing really, really well. And I wanted to share some of the real success stories that we've had with asteroseismology and sort of give you an idea of sort of where we're at, because there are some types of stars that we're doing really, really well at. And there are some sorts of stars that are sort of a little bit more challenging at the moment, shall we say. So I wanted to start with our friendly star, the sun. When you do stellar astrophysics, you always want to make sure that you use as much data from the sun as you possibly can, because we just have access to so much more information from our humble sun. Now, when we study the sun and look at the pulsations in the sun, they're quite different pulsations to the ones I've been showing you, but they do the same sort of thing in the sense that they do bring forward with them information about some of the interior layers of the sun. So I guess people who study the sun and do what I do, they tend to call themselves helioseismologists, from helios, the sun. And helioseismology has been able to get us things like this sound. So we can, make sure that's noisy. So these are pulsations from the sun that have been measured from light, and what they've done is taken that light, those frequencies, and transposed it into something audible. So you can actually hear what the song of the sun is like. I'm sorry if it's a bit disappointing, it's not that exciting. It just sort of sounds like a whole lot of ringing noises, right? What you can pick up though, and I'll play it again if we get to the end, is that sometimes those noises sound like they're getting sort of a bit louder, a bit stronger, and then sometimes they sort of fade away. And that's, again, those frequencies interacting with one another. Sometimes they strengthen each other and sometimes they pull away. So I'll be quiet for a few minutes so you can just listen to that. So I don't think the sun's going to win any awards for original composition there, but it does give you a sense of how this whole music of the stars works, right? You've got frequencies happening there, and that particular signature, it's almost like a fingerprint in a way for the pulsations that are happening on the surface of the sun. And even the surface of the sun, with these pulsations, we can learn some really useful information. And one of the most exciting, I think, results to come out of helioseismology recently is actually looking at how the sun rotates. So this is a cutaway diagram. What you're seeing is kind of a quarter of the sun cut away. So if you're looking at the red area, that's kind of near the equator, and the purple area is up near the poles. And what the colors are representing here is actually the rotation of the sun. So you can, in the red, that means that the equator of the sun actually rotates. It's something like, well, it takes about 26 days for the equator of the sun to rotate. Then, but if you go up to the poles, actually it's a lot slower. So the poles, the surface of the sun takes about 36 days to rotate. It takes about 10 days longer for the pole to go around than the equator. We call this differential rotation. We've known about that for a really long time because we've been able to look at sunspots, and some sunspots, depending on how close to the equator they go faster. So we've known about the differential rotation of the sun for a while, but that's always been measured from the surface. So the question then becomes, well, how deep does that differential rotation go? How fast does the interior of the sun rotate? That's really important if we want to understand just the basic operation of the sun, how the dynamo of the sun works. So, but it's actually a really non-obvious thing to figure out how to measure. But with helioseismology, what they've been able to do is map beyond the dashed line. So that dashed line is going now deeper into the sun. And I think to everyone's kind of surprise here is that actually it turns out that the interior of the sun is just this sort of block of yellow, right? Which means that under the surface of the sun in the interior, it actually rotates all at the same speed. It's all going around at the same rate. So the sun is like a solid marble rotating at sort of this halfway sort of point, maybe about 30 days it takes the interior to go around. But then it's only at the surface you see that differentiation with the fast rotation at the equator and slow rotation at the pole. And we didn't really expect that. We thought it might be kind of quite a complex structure. But actually the sun turned out to be kind of a whole lot simpler than we thought it might be, which almost never happens. So we should be happy about that one, I guess. But yeah, really exciting to be able to figure out the interior rotation of the sun using these helioseismic techniques. And indeed, we've been able to do this on lots of other different types of stars as well, depending on what types of pulsations they have. And then when we go to other stars, what we're trying to understand is how pulsations change the star as it has different points in its evolution. So I'll show you a quick video here that shows you just different evolutionary points of a star and how the sounds that they make can change. You can even imagine this as one star throughout its lifetime. So I'll stop that there, but what that's really trying to show you is that the sound changes as the star goes through its life cycle. So as the star evolves, it gets into larger and larger these big red giants, and that actually changes the frequencies that are happening in the star. And those frequencies, what they're really telling you is that the interior structure of the star has changed. And that's become a really, really exciting part of asteroseismology, is that with these measurements for some types of stars, we've been able to do really precision stellar parameters in like a way that's been just unachievable before. So you might think that you might want to measure some really basic things about a star. You might want to know, what is its mass, for example? What is its radius? How old is it? Those would be three kind of fairly obvious things that you might want to know about a star to understand how it works and how it's going to evolve over its lifetime. It turns out that those are actually, although very, very basic parameters, really difficult to measure for any sort of random selected star that you might choose. And typically when we have done those measurements in the past, we're sort of looking at uncertainties of maybe around 20%, maybe 30 to 40% sometimes for the age. It's really hard to do. There's just, you can't go stick a thermometer in them to measure the temperature. You can't go sort of measure them with a ruler to see how big they are. You're basing a lot of your work on models and how they work. But what asteroseismology is able to now do is give those same numbers, the mass, the radius, and the age, much, much more precisely, because we have these frequencies that are telling us about the interior. So we've been able to knock down the uncertainties on mass and radius of a star down to less than 5%, and age down to less than 10%, which is just incredible. It's like 10 years ago, you wouldn't have believed me when I told you that. You would have said, right, I'm quitting the Zoom, I'm gone, that's it. She's clearly lying. But it has been such a massive revolution. And where it also becomes really important, I mean, these are important things to understand in terms of stellar structure, evolution of the universe, etc., on their own. But our friends, the planet hunters, remember how they sort of said, yeah, hey, you can use that telescope, that's fine. Turns out they really want to know those numbers as well, because if you are studying a planet going around a star, you need to know very accurately what the mass of that star is, what the radius of that star is, and what the age of that star is, if you want to say sensible things about the planet that's going around it. So there's become this really nice back and forth relationship now between planets and asteroseismology, where we are kind of two parts of an even bigger community, if you like, which is, I found really incredible and something I didn't really expect to happen, I guess, in my career. I've become, really best friends with a whole lot of planet hunters. But it's wonderful that that's happened, because we can work together now. So those are all the great successes. I don't want to kind of completely misrepresent this field as saying it's done, we can close the textbook, we just rewrite Sir Arthur Eddington's book, and we can all go home and have a nice cup of tea and a biscuit. I've chosen some really selected examples that we have done really, really well in. These are particular types of stars that we have figured out. They're not the majority by any stretch of the imagination. And if you've done any astronomy, you'll know that there's a whole Hertzsprung-Russell diagram of stars. There are all sorts of different stars, ranging from teeny tiny white dwarf stars to enormous blue supergiants. Now, most of these stars will pulsate at some point in their life, but there's really only very selected few groups of those stars that we've been able to manage to nail down and kind of get this really important data out of so far. And because each star is so different, or each type of star is so different, the techniques that we're doing and the kind of models that we have to use are also different, that, you know, it takes a kind of different concentrated effort to do each group. So the group that I'm working on, we're not quite there yet, but it is really exciting to know that this is kind of on the horizon. And the more and more amazing data that we're getting, then the more and more we're learning, and the more and more closer that we are getting to be able to do this on not just for individual small groups of stars, but actually across all stars throughout their lifetimes. So that's why I sort of like to finish up by saying, well, I think asteroseismology is really looking up. I know it's the typical pun, but I truly believe that. I think we're in this new era of doing amazing things with technology we never even had before. So TESS is flying at the moment. As I say, we've had TESS for 3 years. The stuff we've done in 3 years already has been just amazing. And they're telling us that TESS is likely to be able to fly for another 20 years. So we're just thrilled that we're going to have this amazing space telescope around for a really, really long time. And it's not just TESS, we've also got a new telescope, Plato, which is going to be launched hopefully within the next 3 or 4 years. And Plato is kind of a really souped up version of TESS, doing some really fine detailed measurements of some of these stars. Really exciting. And then of course we've got all the peripheral kind of stuff that's happening in the background, if you like, for us, like James Webb Space Telescope. We've got the EELT, the Extremely Large Telescopes, coming online. So there's a whole new range of I guess hardware that we've got to look forward to coming over the next decade or so. But I made the picture at the bottom actually the biggest, because this is, I guess, the thing that excites me the most. And this is a photograph which actually my student took. This was a student who went out to New Zealand to do some observations in asteroseismology just before COVID, and the last winter before COVID. And yeah, it's, I guess, to me, what's exciting about this is that the number of young people coming into the field, or people who are even transitioning from other fields, because we're quite a young community, I think having new people coming in and doing stuff is just so exciting. People coming in with new, fresh, new ideas. There's a lot of scope to play. And what I really love is the diversity that's coming into the community as well. So we're getting lots more people from underrepresented groups coming into astronomy in general, but it's something I think I really noticed in asteroseismology. Lots of people coming in who traditionally weren't coming into research fields in astronomy. So I find that really encouraging, because they bring new ideas, new ways of looking at things, and that's how we're going to make the most exciting scientific progress. So that's, I guess, the human aspect, I think, which is going to make the next decade super exciting for me. So that kind of brings me to the end of my talk. I hope that I have convinced you, at least on these 2 sentences, that asteroseismology is a fabulous word, and that the study of the pulsations in stars and finding out their interior structures is actually not only, I think, a really interesting part of astronomy, but actually a really worthwhile and really far-reaching part of astronomy as well. So thank you super much for coming along and listening to the things that I've had to say today. I did say that I would show you my podcast. If you're not sick of my voice, which it's fine. If you are, let's I've got to move the buttons to find my tab. There we are. So my podcast that I host with my colleague Chris Stewart is called Syzygy, SYZYGY. We do a semi-regular podcast on just anything that comes up in astronomy or space science that we really think is worth having a good old natter about. We particularly like to dig down into the why should we care? That's my favorite kind of question to try and answer. So if you're interested in audio formats, then we're on all the normal podcast streamers if you're interested in checking us out on there. And we're going to be back from our summer break very soon to record some new amazing things about the universe.